you can hear me and you can see my screen. So, am I audible? All right. Okay, so let us begin to this session. So, for today, I'll be mostly talking about BCS theory. Okay, and we'll look into some detail about ground state of BCS Hamiltonian and also some excitations of BCS Hamiltonian. So let's begin. So at any point, if you have any question, then please feel free to ask. Okay. So for today's discussion, I am actually so it is very hard to find questions for these advanced topics. So I am actually following a note by Daniel Arvas on superconductivity. So which is a very nice note that you can find on the internet. And so this is actually a little bit so this is written in a little bit simpler way than the original book by Schrieffer. So yeah, so I'll be mostly following that. So yeah, so first of all, so let us write the BCS Hamiltonian. So the BCS Hamiltonian is given by this thing. So again, this is a reduced BCS kind of Hamiltonian. So what do I mean by that? I'll just show you. So the Hamiltonian is given by the dispersion, sum over k and sigma, and there is an interaction. So interaction. So this is some effective interaction, and so in BCS, what we assume is that this is because of some effective interaction between electron and phonon, right? So we are not really bothered about how the interaction looks like, but what we need to remember that this is an attractive interaction. Okay, so if there is no attraction, then there is no superconductivity. So this is the interaction, and along with I'll write some terms, so which are like something like this. C right. So this is the BCS theory. So here I am taking the so Cooper pairs has zero momentum, right? So this is a very successful theory for zero momentum. It matches many experiments, but if you want, you can put this Q also, then it actually gives rise to more details, right? So the calculation becomes more involved. So we'll keep the simplest picture. So this is in literature, this is called the reduced BCS Hamiltonian. Okay, so why it is called reduced? Because we are only taking into account scattering processes which happens with q is equal to 0, right? So that's why it is called a reduced. Okay, so now so the main idea, the main thing that we are trying to do is we are trying to diagonalize this Hamiltonian and find the spectra, find the eigenstates and all. Okay, but you can see that so the very so by looking at the Hamiltonian, that see if we only had this part which is a quadratic Hamiltonian, so there is a C dagger C, or you can say this is a bilinear in creation and annihilation operator. So if you have only this piece, then you could diagonalize this Hamiltonian. In fact, it is already diagonalized, right? But as soon as you put some 4 fermion term, then it is not possible to diagonalize in a simpler way. Okay, but we can look into some tricks right to diagonalize this Hamiltonian. So let me actually define a operator which will be useful later on. So it is called a pair creation operator. And which is given by so I am writing this by B. So B dagger K is given by C dagger K up, C minus K dagger so this is a, so what this does is, so this will actually create a pair of electron with up and down spin with k and minus k. Okay, so this is not a Cooper pair, right? So this is just a electron pair kind of, you can think. So up and down and different k and minus k. Okay, so this actually does the job. So then if we write that, and also bk can be written as just the conjugate, so it is just c minus k down, c k up. Okay, so this two pair creation or annihilation operator, we can use these operators to rewrite our Hamiltonian. Okay, so by that I mean that the reduced BCS Hamiltonian now looks something like this. And so in the second term, in the interaction where there is a summation over k and k prime, I'll write directly in terms of this pair creation operators. Okay, so this is kind of reduced in terms of a bilinear, in terms of this creation and annihilation operators of this pair. So now you can so intuitively you can think that, okay, because these operators are made out of two fermions which are spin half, right? So this effectively gives rise to some kind of boson. Okay, so to corroborate that, what we have to do is we have to write down all of the commutation relations of these operators. Okay, so then only you will be able to verify it. But before that, so let us actually do a little bit more simplification. So now so you know that if V is actually a it is negative or it is attractive, then states are actually either not occupied at all or is doubly occupied, because if I want to put a single electron on some state, on some k sigma, then it actually costs more energy, okay, than putting two electrons, because I mean this is a completely different argument than what you had in Hubbard model. So here if you put two electrons in this k and k prime state, because of this attraction, it will actually reduce the ground state energy. I mean, it will give you a lower energy, right? So let me write this. So only single occupancy, okay, only or zero occupancy is allowed, and single occupancy is not allowed. Okay, because this is energetically favored. Right, so yeah, so if that is the case, so in any this k state, we can only put either no particle or zero particle, right? So if you think about that, so then I mean then this becomes clear that if you write something like nk up plus nk down, so this actually okay, so let me write it like that. So this actually becomes something like 2 bk dagger and bk. Okay, so you see what I have done here is I am replacing this nk and n minus k, so which actually appears here. You see this is actually the nk, right? So ek, the kinetic part is ek times nk, right? So here the nk and n minus k appears, and I am assuming that the energy is actually just a quadratic function which is assumed in BCS. So energy goes as some h bar square k square by 2m. Okay, so it is an even function, so minus k also gives you the same energy. And so here what I mean by that, so let's say I have two states so this is my k and this is my minus k. Okay, so the interaction now allows me to put one particle here, and another particle here, right? So now if you count that, so this gives you two particle. So the left hand side would result in 2, right? So the in up and in down is 1 plus 1, so it gives you 2. And on the other hand, so if you think in terms of pair, so you see that there is actually one pair, okay? So k and minus k, they form a pair. So I mean, for each of these 1 plus 1 electrons, I have a single pair. So if I just do a 2 times 1 pair, so then this relation actually makes sense, right? And on the other hand, so this is one of the case when both of the states are occupied, and the other case is when none of the states are occupied. So I have 2k and k prime states, okay, and I have no states, I mean electrons are not occupying any of the states. So then, so the left hand side gives me 0, and also because there are no pairs, the right hand side also gives us 0. Okay, so then, I mean, this relation actually makes sense for attractive interaction. Okay, so we can totally write our Hamiltonian in terms of this pair creation operators. Okay, so now I'll be using this relation and I'll put in here. Okay, so let's see what do I get. So in the H reduced, I have something like this: Ek up Nk plus Ek minus k down Nk down, and there is this interaction term. Right, so and there is a summation over k for the first two terms. So as I said, the Ek is actually even function of k, so E minus k down is same as E of k down, right? So I'll just change the sign, and if I do that, I can take the Ek up common, and I am left with Nk up plus Nk down, and the rest of the term is there. Okay, so now I'll be using the identity that I just wrote above, and it becomes Bk dagger Bk with a 2 factor. Okay, so this is my reduced Hamiltonian. So in literature, this is really written as some H naught, because here I am not allowing any single occupancy, right? So this is written as H naught, and so the rest of the term is given by this summation over kk prime, bk k prime, bk dagger bk prime. Okay, so now you see that by doing all of these manipulations and all of these heuristic arguments, we have actually started from a 4 fermion Hamiltonian, and we have actually reduced in terms of a 2 bosonic bilinear. Okay, so now intuitively you can probably think that this Hamiltonian is something like some alpha bk dagger bk, some sort of alpha k, right, sum over k. So then I should be able to write this in a Hamiltonian in a single particle basis in terms of these B operators, and I can actually do this diagonalization. Okay, but that is actually wrong. So why is that? So let us actually try to see. So now, so if we have a Hamiltonian which looks like this, so then you can think that the eigenbasis will be something like this. So let's call the eigenbasis as capital B, so which is a linear combination, some let's say some dk, okay, so some ck and this bk's, right? So this is one of the linear combination which is, let's say, our diagonal basis, and you can dagger it to make the other linear combination. Okay, so so if this is my eigenstate, so this bk and capital Bk are annihilation operators that annihilates a pair. Okay, so if this bk was bosonic, then this bk would be also bosonic. So let's try to look into the detail of this bk, whether it is bosonic or not. Okay, So to simply answer the question, what we will do is we will try to derive all of the anti-commutation relations, right? Because bosons, they obey anti-commutation. So I'll write something like this. First of all, I'll try to find something like bk and bk prime. Okay, so what is this? So let me actually pull out a nice identity which will be quite useful in this case. So this is actually an identity which so given a four operators, commutator of 4 operators, it actually reduces the whole thing into a set of anti-commutators, okay, which is useful if you are dealing with fermions. And we know that these B's which are pair creation operator, they are made out of fermions, right? So we'll be using this identity. So let's try to evaluate this. Okay, so meanwhile you can also try to evaluate it. So this first thing is given by ck dagger, okay, not a dagger but ck up, ck up, yeah, that's it. And the another one is c minus k prime down, c k down. Okay, so you see this is my four fermion operators, and I can identify all of these operators in terms of A, B, C, D. Okay, so then what I will get is I will get anti-commutation relations like this. So let me write all of these terms. So this is C minus K down, C K up, C minus K prime down, C K up. So from the fermions anti-commutation, you already know that this terms actually vanishes, and similarly you will write the other terms and you will see that all of these things will actually turn out to be some sort of a anti-commutation between this k and k prime, right? And you know that annihilation operators are always they always vanish, right? So which is because of Pauli's principle. So you see that this is actually 0. Okay, so okay, which is a good thing. So we know that the bk and bk prime is actually 0. So this is something that bosons obey. Okay, so this is some signal that okay, these are kind of bosons, but we have to exhaust all possible commutation relations so that we can actually really say, okay, for concreteness. So we'll also try to do this for bk dagger and bk prime dagger. Here also, if you use this identity, you will see that only this C dagger anti-commutation relations will appear, and you know that dagger anti-commutation relations are really 0. Okay, so then this also boils down to be 0, right? So now let us try to evaluate this thing. So bk and bk prime dagger. Okay, so let us take two cases. So let's say when k is not is equal to k prime. Okay, so just to make our life little easy, so then let me write this full thing. So the first one is c minus k down, c k up, and the next one is dagger, c k up dagger, c minus k prime dagger. Okay, so we'll be using the same relation. So the first term is, so let me actually identify all of this term as A, B, C, D. Okay, and we know that so there will be only certain commutations, only certain terms remain which will involve anti-commutation of a creation and annihilation. Okay, creation and annihilation will not survive. Okay, so let's try to write down all of the non-zero combinations. So for example, the first term can be C minus K down, and then I have a anti-commutator between B and C, which here is C K up, C K up dagger, and then I have D, which is C minus K prime dagger. Okay, so this is one of the non-zero term, and then I have so other things are, so yeah, commutation of A and C minus K down, and C K up dagger, and then B is C K up, and D is C minus K prime down. But so here you see that, so this anti-commutation is actually between two different spins, right? So as a result, this will actually vanish. So let's move on. The other two terms are, so there will be a term between B and C, commutation between B and D. So B and D are also they are coming with different spins, right? So that anti-commutation will also vanish. So that term will also vanish. And the last term is, so C is C K up dagger, okay, and there is anti-commutation between A and D, which is C minus K down, and C minus K prime down dagger, and I'll be left with C K up, right? So this is the all possible terms that I can have, okay. And now, so previously I said, okay, so let's actually relax that this assumption. So let's try to do it for general, so it doesn't seem that much complicated. So okay, so let me write all of the non-zero terms properly. So the first one is C minus K down, C K up, okay, and C K up dagger, and plus the second term, and C K up, right? So here you see that, so the first term is already 1, right? So the first term is already 1, so we'll just plug that in. Okay, I have probably missed a prime here. Yeah, B and C, yeah, it should be a prime. Yeah, this first one is a prime. Yeah, so C minus K down, C minus K prime down, and this is delta K and K prime, okay. And the second term is C K up down, C K up, and then again I have delta K and K prime. So there is also, I think I'm missing a prime. Yeah, right. So now you can actually use a trick whenever you have this kind of things, like, so delta is multiplied with some term, so then you can actually change between K and K prime, okay. Whenever you have this kind of a Kronecker delta or Dirac delta is there, you can use the trick and you can write this term as C of minus K down. Okay, I think so I'm probably doing a lot of mistakes, so let me step back a little bit and figure out some things. Yeah, so there is a dagger. Yeah, yeah, that's fine. Yeah, so C minus K, and I can actually change this K prime to be K down, okay, because I have this Kronecker delta nearby. And for the second term also, I'll change this K to K with K prime. So now we see that this is actually a nk up, right? So this is a number operator for the K mode and spin up. So this is fine. And on the other hand, I have this term which is not nk, but this is actually 1 minus nk. Is this fine, or just one thing? Yeah, so I have actually messed up a minus also. So the second term is actually minus. Yeah, So now this will work out. So then I can flip this CK dagger, okay, and this will give me a 1 minus CK down dagger and C minus K down with a delta KK prime. So you see that this is also a NK, so I'll directly write it as 1 minus NK down meeting. Yeah. So NK up K prime. Alright. So yeah. So let me actually write this thing. Yeah. So as I have shown you, this BK and BK dagger, this commutator is not actually 1, but it is actually 1 minus NK down minus NK up with a Kronecker delta, right? So this becomes 0 only when K not is equal to K prime. So when K not is equal to K prime, then BK and BK prime dagger is actually 0, okay? But if K is same as K prime, then you don't get 0 anymore, okay? So this is not a bosonic commutation, right? So because for bosonic commutation you always expect that A and B will be something like, so A and A dagger will be 1, okay? So but here we don't see that. So this particular piece actually spoils the commutation, right? So these are not perfectly bosons, so we actually cannot diagonalize this Hamiltonian with a linear combination of these B's, okay? So if we just find a linear combination of these B's like I mentioned before, so we cannot diagonalize this Hamiltonian, okay? So we have to find some another way. So this is a very important point to, I mean just to see that not always you can diagonalize this kind of Hamiltonian, because these are not pure bosons. So these are made out of electrons, and electrons under the hood they obey Pauli's exclusion, okay? So when you write B's in terms of these fermions, that also brings up those Pauli's exclusion, which is seen in this term, okay? So yeah, so this is not purely boson, okay, but so there is something that will help us. So let us try to calculate this kind of an operator. So let's say, so BK dagger square, okay? So BK dagger square, so let's try to evaluate it. So it is CK up dagger C minus K down dagger times CK up dagger C minus K down dagger, okay? So now so when you write this expression, so you see that you can actually do one exchange. So let's exchange these two creation operators, okay? So I'll get a minus, but that's fine. So CK up dagger and C minus K down dagger and dagger. So you see that, so I am getting something like the CK up square and C minus K down square. So, but you know, for fermions, this when you square a creation or annihilation operator, that is basically 0, right? So that is again because of Pauli's exclusion. So this is 0. So B square is actually 0. So this will be helpful to find the ground state, okay? So okay, fine. So now we see that, okay, by writing in B we have not actually solved the problem, but we have introduced some new complications. So now let's try to do another simpler thing, which is the mean field theory, right? So in these interacting theories, the simplest thing that you can do is a Hartree-Fock kind of mean field theory, okay? So we'll again try to do a Hartree-Fock and try to do this diagonalization, okay? So yeah, so any questions up until now, please feel free. All right, okay, so now let's start the mean field calculation. So let us start with our this reduced BCS Hamiltonian, which is given by this dispersion E k sigma C k sigma dagger C k sigma summation over k and sigma, with the interaction term given by bk prime and this bk dagger bk prime. All right. Now, so when we'll do mean field, so we'll have to assume that okay, something is actually obtaining a mean value and we have a fluctuation around that mean value. Okay, so what we will do here is, so we'll say that our bk, so we are writing our bk in terms of a expectation value, okay, with an additional fluctuation term which looks something like this. So you see, I have just added and subtracted this term, right? So I have not actually changed a lot, but so we'll see that where we go with this. So this term is called the fluctuation, so I'll write it as delta bk. Okay, so bk operator is written in terms of bk expectation plus delta of bk. Similarly, I'll also write for the bk dagger, so which is bk dagger expectation plus delta bk dagger. Okay, so I'll plug this expression into my reduced BCS theory, and I'll keep only up to order delta bk. So that is order of delta bk. Okay, and so we'll say that the delta bk square term is negligible. Okay, so we'll just plug 0 for delta bk square terms. Okay, so yeah, so now let's try to put this thing in the interaction. Okay, so let us just focus on the interacting part for now. So there is k and k prime, and I have b k k prime, and I'll just substitute in place of b and b bk and bk dagger. I'll just plug these expressions. And the other term is bk plus delta bk prime actually, yeah. And so next thing is just to expand out all of the products. Plus I will have delta bk dagger bk prime expectation. So I'm just doing this multiplication, and I'll have bk dagger expectation delta bk prime, and I have delta bk prime. Okay, so this thing, because this is already delta b square, so I'll just ignore it. I'll just put it 0 in place of this. Okay, so now so we'll replace back our delta bk. So delta bk is what? Delta bk is given by bk minus bk expectation. So I mean, this is the way all mean field theory works. Okay, so I'll just replace it back. So delta bk dagger is given by bk dagger minus bk expectation, right? So this is just the delta bk which I have just replaced back from the previous equation, and I have bk prime expectation. And for the other term I have similarly so bk dagger expectation and bk prime minus bk prime expectation. Okay, so now simplify this even, try to simplify this even more. So if you expand all of these terms, you will see that it will become simpler. Some of the things will vanish. Yeah, so now you see that this term will actually cancel with this term, okay, and the rest of the terms will be there. Mm, yeah, bk, and I have this constant term, okay. So you see that this has actually boiled down to a nice form, and this bk are now, these are two fermions, these are bilinear infermions. So now we have some hope of actually diagonalizing the Hamiltonian. So normally it's just note a thing. So normally if you have some operator like a times b, and if you are trying to do a mean field, so you will always get a expression like this. So you'll get, so like a expectation b plus a times b expectation and minus the average a comma b, okay. So you can think that, okay, the mean field is like a linear operator which first acts on this one and then acts on this one, and then you have some correction, okay. I mean, this is like this is how all the mean field works. So if you talk about Ising model, if you talk about Hubbard model, all of this thing works like this. This is the standard mean field. So yeah, so this is the same form, okay. So now let's pull all of the pieces together and write the mean field Hamiltonian. So our reduced, so mean field Hamiltonian, so MF superscript is that stands for mean field, so is given by the dispersion term, so our k and sigma plus I have this other terms. So let me actually copy this back. So now you know what we can do is we can replace these b daggers in terms of c operators, okay. So let's do that. Yeah, okay. Okay, and then I'll be replacing just fermion operators in place of this bk daggers and bk. So this becomes ck up dagger, c minus k down dagger. So expectation with c minus k prime down, c k up. So then the second term is c k up dagger, c minus k down dagger, and c yeah. So then this becomes ck prime c minus k down, c k prime up, okay. And then I am left with the other term, so which is just these two terms. There is a minus, yeah. So now we can actually so now let's try to introduce our mean field gap parameters. So I'll be calling this thing as my gap function, okay. So let me actually write this in terms of a gap. so that the single particle picture becomes very apparent. Okay, so yeah, so let me first write it. So this is delta at k. So I'll also write it as delta k star, and I'll just keep this last term, I'll just keep it same, and then I have k prime. Okay, so you can see that, so this is not like a normal fermionic Hamiltonian, but here we have ck dagger and ck dagger, okay, which you probably already know how this mean field Hamiltonian looks like. So, and this is a constant piece, right? So the constant piece actually changes the ground state energy, but it doesn't do anything else. It doesn't change the eigenstates, or I mean, it doesn't do a lot, but it is there. So if you are trying to find the ground state energy, then this is something important that you have to keep track of. Okay, so now what we can do is we can try to diagonalize this single particle problem. Okay, so yeah, okay, and so the gaps, what I have written, so the gap equation is given in terms of something like this. So delta k is given by sum over k prime p k k prime and expectation value of c, it's a k, okay, c k prime dagger, k, c minus k prime, and c k up. Okay, so this is my gap equation. Okay, so basically so this mean field is, I mean, so this is like a normal mean field, right? So you know there is some kind of molecular field in which all of the other particles are moving, so right. So now the task is to solve this delta k. So this will give you the gap of the superconductor. Okay, and so for BCS theory, it exactly boils down to the BCS gap. So we'll try to derive that gap equation. But so before that, we have to actually diagonalize the rest of the Hamiltonian, right? So the rest of the Hamiltonian means this whole part. Okay, so let's try to do that. Okay, so this constant term is there, but I mean, so this will not do anything to the diagonalization, so we'll just keep this apart for now. Okay, and we will just focus on the single particle term. So single particle term, so what we'll have to do is, okay, so let me first try to write it. So let me first expand out the spin summation, right? So spin summation will give me this c k up dagger c k up, and plus I'll have e k down, c k down, and c k down. So here I'll do a little bit of manipulation for the dispersion term. So what I will do is I'll change this. So in this part, in this second term, I'll change k to minus k. Okay, so what happens if I do that? So it becomes epsilon minus k, it becomes c minus k down dagger and c minus k down. Okay, so and because I already said that this is I'm measuring a quadratic band dispersion, so minus k is same as k. Okay, so I'll just write it as C epsilon k of spin down. Okay, so this is so I've just removed the minus sign from here. Okay, and I'll also like to interchange these things, so for reasons which will be clear in a moment. Plus epsilon k down and C minus k down, C minus k down dagger, and there is a minus epsilon k down. Okay, because of the anti-commutation I get this one, right? So there is a summation over k all over the place. Okay, now so what I want to try is I want to write this in a Hamiltonian in a basis which looks something like this. So the basis looks something like this: ck up and C minus k down dagger. Okay, so in superconductors this kind of basis is always adapted. So this is called a Nambu basis. So which is so what happens is, now because of this kind of anomalous terms in our Hamiltonian, so now I have to write in a larger basis which is a particle hole basis. Okay, so if I didn't have this term, so like for any normal fermion, if I only had this, then I didn't have to do that. But now you see that these are essentially couplings between particle and whole sectors. So that's why you have to actually keep these terms. I mean, you have to write this in an enlarged basis. So psi is this, and psi dagger is ck up dagger and C minus k down. Okay, so let's just quickly write it. Okay, I think I missed this minus here, and this is plus E. Yeah. So the mean field Hamiltonian now can be written in this form: ck up dagger, C minus k down with epsilon k on the diagonal and minus epsilon k on the other diagonal, and delta k and delta k star. Again, plus there is some constant, right? So now this is the whole Hamiltonian. So now when you have written it in a way like this, and we see that this is just a 2×2 fermionic Hamiltonian, right? So for fermionic Hamiltonians, we can actually quickly write a unitary transformation for this 2×2 Hamiltonian, and we can do the diagonalization, right? So now so I can write a diagonal Hamiltonian, right? So for that, let me use something like this. So gamma. So now I'll call our diagonal creation and annihilation operators to be gamma. Okay, so the gamma will be something like this, or let me write it as this: C k up and C minus k down dagger. So I'm trying to write a very general unitary transformation that will diagonalize any 2×2 Hamiltonian. Okay, so then you can check that. So if you choose your Hamiltonian like this, okay, okay, so the matrix that I have written is actually a element of SU2 group. Okay, so this is the most general matrix you can write. So any other matrix that you can write will always be related to this thing by some unitary transformation, by similarity transformation as well. Okay, so this is a SU2 matrix. So this belongs to SU2. Okay, and so till now this theta and phi are so these are like parameters. Okay, we are not still sure what this theta and phi should be, but so the main task now at hand is to figure out what this phi k and theta k is, such that this kind of matrix diagonalizes this Hamiltonian. Okay, so that is all what we're trying to do right now. And so this has to be unitary. So why is that? Because this has to be unitary. So because unitarity actually preserves the anti-commutation relations. So this will preserve anti-commutations. Okay, so because this is unitary, so I can also do the reverse transformation. So reverse transformation is just the dagger. So the gamma k up and gamma minus k down will be given by just the dagger of this matrix, right? And sine theta k e to the power I phi k and cos theta k. So here so the unitarity actually restricts that the theta k and phi k, they belong to real, so they are all real numbers, and this acts on ck up and c minus k down dagger. Okay, so let's actually for convenience, let's actually call this some u matrix. Okay, so u of k. Okay, and this is our u dagger k. So now I'll plug this linear transformations into this mean field equation. So you see that it will actually become something like this. So this is my psi dagger and this is my psi, right? So I'll replace it with uk times gamma k up gamma minus k down dagger with this matrix epsilon k delta k star and minus epsilon k, and on the other hand I have this uk dagger gamma k up dagger and gamma minus k down. Okay, so I am assuming this that this Hamiltonian is diagonal when I write it in terms of gamma. So that means that so this now rotated Hamiltonian or this unitarily transformed Hamiltonian is now diagonal. So that actually basically means that this whole thing will reduce into some diagonal matrix. Okay, so now let's see what do I so if I write everything explicitly, what is the thing that we get. Okay, so let me write all of these parts carefully. So I have this 3 matrix multiplication, right? So you can go ahead and do that. So I think I'll just directly write the result. So okay, so let me just write out the result here. So this is a very long expression, so let me, so I'm dropping the k's for now because it is a lot of so just for brevity. Okay, all right, so one thing is that, okay, so one important point I forgot to make. Okay, so let me, yeah, so now you see that when, because of mean field, I now have this kind of terms, right? So what happens if you act this on a vacuum? So or this on a vacuum. So what happens is this kind of operator doesn't conserve the number of particles in the system, right? So because it either creates two particles or it destroys two particles. Okay, so so uh, so what we need to do is, so we till now all of the expectation values and all of these things, we are assuming that we are working in a canonical ensemble. Okay, but because the number of particles are not conserved anymore, so we have to actually get into grand canonical ensemble, right? So if I do that, so in grand canonical ensemble, what I will have is so I'll define uh, the grand canonical Hamiltonian something like in a way like this: k is equal to h bcs mf minus mu times n. So n is the number operator. Okay, so if I do this substitution, then actually in the diagonal my ek's are replaced with ek minus mu. Okay, so mu is the chemical potential, and this also gets replaced by minus mu. Okay, and this whole thing in literature it is sometimes defined as some xi of k. Okay, so yeah, just a important point. So I'll just write xi k in this place of epsilon k, right? And now let's look at the form of this multiplied matrices. All right. And I have so similarly I have, so this is Hermitian conjugate of this one, and then I have a similar kind of term here as well. Yeah, so you see that, so because we have not fixed the theta and phi yet, so we have four terms in the Hamiltonian. So this is my it's a 1 1 term, this is my 1 2 term, this is my 2 1 term, and this is my 2 2 term. So now for this Hamiltonian to be diagonal, so 1 2 and 2 1 should be 0, right? So that will actually give us the values of theta and phi. Okay, so that means so for the diagonal or diagonal part to be 0, we have to satisfy this equation. Okay, so all of these things are, by the way, k dependent. Okay, but I am just not writing the k now. So you see that this left hand side is xi sine twice theta, and the right hand side is delta cosine 2 theta. So this gives me, so tan 2 theta should be delta by psi. Okay, so if I know this tan 2 theta, then from the trigonometric identities we can actually write what the cosine of 2 theta is. So xi by e, and sine of 2 theta is delta by e. So where this delta e is given by xi square plus delta square root, and also the phi is argument of delta. Okay, so if I choose our phi and theta is this in this fashion, then our Hamiltonian will be diagonalized. Okay, and the diagonalized Hamiltonian, which is given by this, so k tilde, so k tilde is given by this uk dagger, let's say this h of k and u of k. So this will be something like this. So it should be clear if you just plug back all of these things back in this off diagonal Hamiltonian. You will see that this will vanish and this diagonal will simplify to become just e or minus e. Okay, like this. So now this is in the proper diagonal form. Okay, and we can, if you want, you can restore all of the k's. So phi of k is now argument of delta k, and 2 theta of k is xi k by so delta k by xi k, and so on and so forth. Okay, so you can just do this for all of the other relations. So we have now diagonalized this whole thing. Okay, now so let's try to see now how does the total mean field Hamilton looks like. Okay, so let me write it as k BCS. So k BCS now looks something like this. So E k gamma k sigma dagger gamma k sigma sum over k and sigma. Okay, so now see this, so this is my diagonal part. Okay, and I had some constant pieces, so which I will have to bring back. So plus summation over k xi k minus e of k minus the constant term which came from the mean field. Okay, so this is my whole Hamiltonian. Okay, so I have this single particle part and also this constant part. So now so ground state is actually defined by this identity. So ground state means that if I have an annihilation operator at any momentum or sigma, when that acts on the ground state, that should be 0. Okay, so that is the definition of ground state. So now if I'll be able to find a ground state like this, which is annihilated by this gamma, then you see that this term will actually go away. Okay, and we will be left with only the second part. So this term is actually, so this has nothing to do with the ground state energy. So this term actually gives rise to some excitations. Okay, so some excitations above the ground state. So we'll see that what that is. So now the question is, what does the G look like? Okay, so this G, so actually, so this is uncharged by Schrieffer. So who told that the G will be something like a coherent state. Okay, coherent state of the pair creation operator. So G is something like this, some normalization, and then there is e to the power some gk and bk dagger acting on vacuum, and there is a product, right? So now, as I already showed you, that bk square bk dagger square is 0, right? So if you try to expand this out, the exponential, so you will see that actually truncates up to the first order, right? So this becomes 1 plus gk bk dagger acting on vacuum. Okay, so because I don't need to write any other terms, because bk square and all next orders are 0. Okay, now you will see that if you write the form of gamma and you take this G, you will say this is truly a state which is annihilated by gamma. Okay, so this is a ground state. Okay, so if you normalize it properly, you will see that so this G is actually given by it is not a normalized, right? So this is 1 and this is gk, so this alpha is a normalizing constant. So you can normalize it and you will see that so this becomes something like this: cosine of theta k minus sine of theta k times e to the power I phi k. And I can write the pair creation operator. And the whole thing acts on vacuum. Okay, so this is the BCS ground state. And this theta is this phi are the arguments of your order parameter or the gap, or these thetas are the other order parameters which we use to diagonalize the Hamiltonian, right? So in principle we now know everything that we have to know, and we can calculate any expectation values by taking expectation on this ground state, right? So now one can actually think about this ground state in a more detail. So what does this this operator actually do? So what it does is so you will basically see that there are two terms in this thing. So this term dictates what is the probability of double occupancy. Because this is precisely the pair creation operator, and so this first term tells you that probability. So if you mod square, then only it is probability of zero occupancy. Right? So just to give you a physical picture, so what happens is, like, let's say you have some field pharmacy. Okay, so this is your EF, and what this does is, so the second term, what it does is, so on the vacuum it starts to create two pairs of particles, so one in the upspin and one in the downspin with opposite momentum in a way like this. Okay, so the full pharmacy gets generated with this second term, this creation operator. Okay, and this tells you what is the probability of zero occupancy. Okay, so now, so there is a subtle point here, that so this pair creation is not actually a BCS, not actually a Cooper pair. Okay, so when you are really at very low energy, so this is just a normal electron hole pair at the very deep in the pharmacy. That is just a normal electron hole pair. So only when you are within so let's say only when you are within some very small width of this Fermi energy, which is given by the d by energy, which is h bar omega d, so then only this kind of pair creation operator becomes a Cooper pair. Okay, so this distinction is really very important. Okay, so yeah, so now so because okay, we have done so much, we have also we could actually get some idea of the ground state. So then it is really important to check that whether this is the correct answer or not, the correct answer to the ground state or not. Okay, so how do you check that? So to check that, what we will do is we'll go to a normal metal limit. So how do we achieve that? So in normal metal, the delta k's are all 0. So wherever we have plugged in our delta k's, we'll just put 0 in all of the places. Okay, so if you'll do that, so you will see, you will see that, and the temperature is also 0. Okay, so in this limit you will see that this yeah, so cosine k was what? So cosine of theta k was given by or yeah, so let me actually write that. So cosine of 2 theta k was given by psi k by ek, right, and sine of 2 theta k was delta k by ek, right. So when you actually turn this off, delta k goes to 0. So what will happen is, so the cosine 2 theta k, so this is just psi k by psi k square plus delta square root. So what will become is, this becomes psi k by psi k mod. Okay, and so this basically becomes a Heaviside theta function with theta of k minus kf, and the sine 2 theta. So if you take the limit carefully, sine 2 theta becomes a delta kf minus k. Okay, so this is what the these two parameters, so two parameters of the wave function, they become in a metal. Okay, so if you want to plot it, so let's say this is my momentum direction and this is my kf. So before kf I only have this cosine of theta, so this becomes just this Heaviside function, and after k this becomes 0. Okay, so this is the picture at temperature 0. If you will turn on temperature, then you will see that this actually will smear out. Okay, so this is cosine theta k. Okay, so one important thing I have missed here. So the cosine theta k actually looks a little bit different, is ek plus 2 ek. So if you just take this expression, so you know already what the 2 theta k is, so you will be able to write down what the cosine theta k is. Okay, so cosine theta k is this, and sine theta k is given by ek minus ik by ek, and so ek's are ik square plus delta square. So in the limit delta going to 0, this becomes just mod ek. Okay, so if you take this limit, so you will be able to see this Heaviside theta functions. So this is cosine theta k. So beyond the Fermi momentum, it vanishes. Okay, and the other so the sine theta k is slightly different. So it is 0 up until the Fermi momentum, and then it picks up at exactly Fermi momentum and it becomes constant. Okay, because it is just a Heaviside theta function, right? So just to remind you again, the cosine theta mod square, so cosine theta k mod square, so this is the probability of double occupancy and sine theta k mod square is the probability of single occupancy. Okay, so this means that, so below kf, so you can take this two you can have this double occupancy, right? So because this is 1, and beyond kf you have no more double occupancy, you have only single, you can only have single occupancy. Okay, something like that. So this Heaviside theta functions appear at a normal metal. Okay, but as soon as it becomes superconductor, so then this will actually smear out a little bit. So let me So this will smear out a little bit, and the other one will also smear out. Okay, so these two things are for superconductor. So this is one clear distinction between a normal metal and superconductor, and we have just checked that, okay, even if we have superconductor and if we go back to normal metal limit, then we can make sense of the result. So then we get the field pharmacy, something like that. Okay, so yeah, this is one of the point. Yeah, right. So we have calculated the ground state. Okay, now so we have actually not talked about the gap equation at all. So now let's talk about this gap equation. So normally the gap equation has to be obtained self-consistently. So what do I mean by that? So let's try to see. So this is our gap equation, and the number density, or the number of particles, is given by this kind of a term, Ck sigma dagger Ck sigma. There is some sigma as well. Okay, so now the task is to obtain these expectation values. Okay, and we will see that these expectation values will actually appear in terms of delta k's. Okay, and so you have to actually solve it self-consistently. So the meaning will be really clear soon. And so we have to solve both of these equations self-consistently. So this n, so this is also important because we are working now in a grand canonical ensemble, and this will fix the chemical potential. Okay, so yeah, so both these equations has to be solved simultaneously. Now if you want to calculate this expectation value, so what we would like to do is we'll express this C and C dagger in terms of the diagonal, in terms of the gamma daggers, right? So let me remind you what that was. Yeah. So Ck, let's say C K sigma dagger is given by cosine of theta k gamma k sigma dagger minus sigma sine theta k phi k and this k minus sigma. So if you think about it, so the Ck dagger, it actually creates one particle with up and sigma, and another particle, another hole with down and sigma bar or minus sigma, let's say. Okay, and minus k as well. So this is what this C dagger creates. Okay, and it is actually, you can say this is actually a mixture of a electron and a hole. Okay, so which becomes clear because the Hamiltonian that we have started with was a Hamiltonian in particle and hole basis. So that's why we actually end up with a combination which entails that particle and hole structure. So we have this Ck dagger. Okay, and so we like to calculate these expectation values. So the expectation values are given by this, and these are all grand canonical ensemble average, right? So we have that in back of our mind. The first term is cosine of theta k gamma k sigma dagger minus sigma sine theta of k e to the power minus I phi k gamma minus k minus sigma. So this is for the first term, and for the second term we'll substitute cosine of theta k gamma k sigma minus sigma sine theta k e to the power I phi k gamma minus k minus sigma dagger. Okay, so this is the whole expression, so we can now simplify it. So the first term will become something like this: cos theta k square gamma k sigma dagger gamma k sigma plus sine theta k square gamma minus k minus sigma and gamma minus k minus sigma dagger expectation. And we also have the other terms which are like cos theta k sine k gamma k sigma dagger gamma minus k minus sigma dagger. Okay, and then there is minus sine theta k cosine k. I have actually missed one e to the I phi k here. Okay, and this expectation and the other expectation gamma k sigma dagger gamma minus k, what I'm doing, gamma minus k minus sigma and gamma k sigma. Okay, so and there is also e to the minus I phi k. So you will see that these two terms will actually vanish because our Hamilton is diagonal in these things. Okay, and this kind of correlations are not there at all in a diagonal Hamiltonian. So you'll be able to show that this last two terms will vanish. Okay, and so this gamma k sigma expectation value in a grand canonical ensemble is given by the Fermi function, right? So it is given by the f of ek, so which is nothing but e to the power beta ek plus 1. Okay, so I mean, just remember that always you assign this funny functions to this diagonal things, to the diagonal number operators. Okay, so off diagonal operator doesn't have any funny function at all, right? So if you do that, then so this becomes, the first term becomes cosine of theta k square and then funny function, let's write it at fk, and then the second term becomes sine theta k square, and so you see that there is a gamma and gamma dagger, so I can okay, so basically it becomes 1 minus f of k. Okay, so yeah, so if you simplify it furthermore, you will see that you will get something like this: half minus psi k to e of k tan hyperbolic 1 by 2 beta ek. Okay, so this is this expectation c k sigma dagger c k sigma, and you see that that expression is actually independent of sigma, right? So none of the sigma appears here. So now if you try to draw this thing, sorry, so if you try to plot this quantity, so you will see that you don't get any more a funny function, right? So even if this looks like operator, but remember that this is not the diagonal basis. So the diagonal basis is gamma. So if you try to draw this quantity, so gamma k sigma dagger gamma k sigma, you'll get a funny function, right? But if you try to plot this quantity k, okay, so this is kf k and this is kf. If you plot this quantity which is c k sigma dagger c k sigma, you will see that you will get something like this. So something like a smeared out Heaviside theta function sort of. Okay, and So this is what you get even at T is equal to 0. Even at 0 temperature you have this smearing. So this happens because of, now you have formed a gap because of the attractive interaction. So now this smearing out is given by, so this smearing out is given by, so delta naught by EF times KF. This is of the order of this. Okay, so this is present even at 0 temperature. Okay, and this is coming because of interaction. Okay, all right. So and the other term, so we have obtained this kind of expectation value, right? So now we still have to obtain this kind of expectation value. So the protocol is same. So we'll write this in terms of the gamma operators, and we'll just expand it out, and we'll see what we get. So the other term, which is C minus K minus sigma and C K sigma. So let me just write out the expression. So this is for the first C minus K minus sigma, and then I'll have the next term, okay. So you can expand it out, so I'll directly write the result. So you will see we'll get something like this: sigma sine of theta k cosine of theta k and I phi k. So if you just replace, if you just put back the funny function in place of f of k, then you will get a simpler expression. Okay, so this is what the expectation value of this kind of thing is. And so you see that the scheme is actually pretty simple. So given any sort of this kind of combination, any C dagger C or any of this kind of combination, you can actually calculate this thing as well: C K plus Q dagger sigma C K sigma. So this is called a charge density wave order. Okay, you can just plug in the gammas and you can try to find the expectation values. Okay, so the scheme is pretty simple. So let me write out all of the expression that that I started with. So the number is given by half minus xi. So yeah, let me directly put it: 1 minus xi k by ek tan hyperbolic half beta ek summation over k. So this is the number. Okay, if you just calculate this quantity, you see we have reduced all of the expectation values into this kind of simpler quantities. Okay, so we know ek, we know xi k, we know this thing, and if we know all of this, we know the number. Okay, and the gap is given in terms of in terms of this thing, delta prime to ek prime tan hyperbolic half beta ek, and there is this interaction term b k k prime. Okay, so this is the full expression, and let me actually just remove this delta. Yeah, so we have reduced the this operator expectation values into this just simpler expression. Okay, so now you see that this actually becomes a self-consistent equation. Okay, so you give a delta k prime, so it will do some computation and it will give you some delta k. Okay, so and you do this until the result doesn't change anymore. So you go back and forth, back and forth, back and forth. Okay, so you do this until the result doesn't change, okay. And then when this delta k doesn't change, you call this to be a solution, or you call it to be the real gap, okay. So this is the full self-consistent loop. So normally for BCS theory at least, so the VKK prime, so it is assumed to be minus V, okay. And now if this xi k is less than h bar omega d, so this is the Debye energy, and xi k prime is less than h bar omega d, so otherwise this is 0, okay. So you can take a very simple form, and then the calculation of this gap becomes easier. But if you do not take this form, if you take some complicated kind of expression, then this cannot be done analytically. So then you'll have to take some numerical help, okay. So now, so this is all these equations are for finite temperature. So you can go to zero temperature solution just by putting beta to be infinity. Oh, okay, beta to be infinity. Beta infinity is T0, right? So beta is the inverse temperature. That's why T is 0. So if you do that, if you plug this back in the number and gap equation, you will see that the number of particles is given by 1 minus xi k by E of k, and this gap is given by bkk prime delta k prime and 2 ek prime, okay. So it becomes a little bit simpler. So now we can try to solve this thing, right? So we can now solve this gap equation. So the gap equation, so normally typically so this delta function or this gap is actually non-zero only when we are within the small shell of Debye energy, okay. So the condition is that this actually reduces the phase space where we can have the integration. So that means if you have a circular Brillouin zone or circular Fermi surface, then so there is a very small energy window where this gap equation is actually non-zero, okay. So this width is given by the Debye energy, where omega d is the Debye frequency, right? And if you go out, then this is just 0. Okay, so now let us plug in the form of the VKK prime and we can do this integration. So I get V by capital V sum over k and d3k and 2 pi whole cube delta by 2ek and theta h bar omega d minus xi k, okay. So this imposes this condition, this actually imposes the condition, this one, okay. So now what we can do is we can basically convert this 1 by v and summation to a momentum integration. So it becomes d3k 2 pi whole cube delta by 2 ek and heaviside theta function xi k, okay. So now we can change this momentum integration to energy integration by introducing this density of states. So then this integration becomes something like this: d epsilon g of E, and then this becomes delta by xi square plus or let's say E square plus delta square, okay. So I have changed this integration from a momentum integration to a energy integration. Okay, so this is the same, just the discretization is different. So in this case the discretization is over this whole 3D space, and in this case the discretization is along this energy axis. So if you have some energy axis, so you I mean you go along, you discretize along that that direction, and you will get the same integration. So, and the Heaviside theta function will give me a cutoff to this integration. So this integration is now limited between 0 to h bar omega d. Okay, and because this so we are near the Fermi energy, and near the Fermi energy we can actually take out this density of states. So I'll just write it as a g of E of f. So E of f is the Fermi energy, and so the rest of the integration we can do analytically. Okay, so if you do that, so you will get something like this. So here also there is delta. So delta will cancel out from both of the side. Okay, because I am assuming it is constant, it doesn't depend on energy anymore. So then you will see that you will be left with 1 is equal to half V density of states at Fermi energy, and integration over h bar omega d by delta 1 by 1 plus s square to the power half. Okay, so I have also redefined my d epsilon, and I have divided with delta actually. So now the integration becomes dimensionless. Okay, so then you get Vg of epsilon f times sine hyperbolic inverse So yeah, so now we can do a little more simplification. So we can actually approximately write this expression. We can invert some of the things, and it becomes 2h bar omega d exponential minus 2 by g ef times v. So here this small v is the interaction strength, right? So it is the attractive interaction strength, right? So here there is an important point I'm trying to make here is, so you see that the delta naught actually depends on e to the power minus some 1 by v. Okay, so that means that even if I have a very small attractive interaction, so if I have a exponential, very small attractive interaction, then also I'll get a finite delta naught. Okay, so to draw a contrast, so I like to remind you about the Stoner criteria. So Stoner criteria is a theory for band magnetism. So when we have some bands and we apply external magnetic field, okay, so when do you get a ferromagnet? Okay, so that is what Stoner criteria dictates, and it tells us that if our repulsive interaction times the density of states at Fermi energy is greater than 1, so then only we have a ferromagnet. Okay, so this g of density of states is actually approximately 1 by the bandwidth. So one actually talks about whenever u is greater than omega, so then we'll get a ferromagnet. But see, on the other hand, so for the superconducting gap parameter, so we have some exponential e to the power minus something sitting here. Okay, so even if v is very small, 10 to the power, let's say minus 13. Okay, even if v is like really very small, then also we'll see that, so this will actually give a finite value to this delta naught. Okay, but on the other hand, for this Stoner kind of instability, so these are called instability. So this is on the left hand side, I have BCS instability, and I have on the right hand side I have Stoner instability. So they are, I mean, they are different in the sense that if I have any small interaction, that will not give rise to a ferromagnet, so I'll have to crank up the interaction up to a certain point, let's say up to the bandwidth, okay, then only I can have a ferromagnet. But on the other hand, for this BCS instability to happen, I can have a exponentially small interaction that will also give rise to superconductivity. Okay, so these, I mean, these are two different classes of instability. I mean, just, I mean, so that you can see the contrast. Okay, all right. Okay, so one other thing is, yeah, so we were talking about this this factor sine theta k and cosine theta k. Right, so these are in literature, they are called coherence factors. Okay, so these are called coherence factors, and so these coherence factors are actually almost okay, so as I draw it before, so at kf, so this is the Fermi momentum, at kf only the coherence factor changes somewhat, but far from this kf this is just +1. So this is our sine theta k, it's a square, and this is our cosine theta k square. Okay, so yeah, so you see that far from the Fermi momentum, this is constant, this doesn't change at all, and it changes significantly only around this kf. Okay, and this is a signature of this superconductivity. And as I already mentioned that if I do not have any superconductivity, then this becomes precisely a step function. Okay, so that way you can distinguish between the normal metal or a superconductor, right? Okay, and yeah, and also, so you probably remember that, so in our BCS Hamiltonian, so K BCS, we had something like this. We had something like this EK gamma K sigma dagger gamma K sigma plus K xi K minus EK, and there is additional term summation over K and K prime, B K and K prime, C K up dagger and C minus K down dagger times C minus K down C K prime up, right? So and I told you that, so if I am looking at the ground state energy, so E0, so then I'll throw this away. Why? Because my ground state energy is defined in terms of a ground state expectation value of this K BCS. Okay, and the definition of these gammas, or the definition of the ground state, is that it annihilates this ground state if you just act this gamma K. So if that is the case, the ground state energy is just given by sum over K xi K minus EK minus K comma K prime right. And so you can you can again calculate these things, because you know what does this expression look like in terms of gamma, right? You can plug those expressions. Yeah, so you can plug those expressions and you can simplify this furthermore, but this is basically what the ground state energy is. Okay, so now let's say if you are asking, okay, we know the everything about the ground state, so what happens to the what happens to the excited states? Okay, what happens to the low lying excited state, or what happens to the excitations? So to answer that, you need this piece. This becomes important at that point. Okay, so this actually gives rise to, I mean, quasi particles. So these gammas are creation and annihilation operators of quasi particles. So these are fluctuations, or these are some particles, I mean, above the ground state, right? So as I said that this, as I showed you, that this Ek was given by xi k plus delta square, xi k square plus delta square, right? So you can plot this this thing. How does it look like? So these Ek are precisely the excitation energies. So this is precisely the excitation spectrum. Okay, so how do you draw that? So to draw that, there is a nice trick to draw this thing. So first you draw the particle band, so which looks something like this, k square, and let's say this is your EF. Okay, and then you invert it. So if you invert it, it becomes something like this. Okay, now so now see that, so your so this is your Ek, and this other thing is your minus Ek, right? And you see that the delta actually introduces a parameter between these two bands, right? And from degenerate perturbation theory, you know that whenever you introduce this kind of new matrix elements, it will open up a gap. So in presence of this delta, your this thing looks something like this. Okay, and this energy is given by the delta. Okay, so this is your delta. So you see that away from the this gap, so this becomes particle like, right? So this becomes particle like because again from the coherence factor you see that this is just a constant. Okay, so this was a signature of a normal particle. Okay, so away from the Fermi energy, it becomes a particle like excitation. And so in this, if you are in this branch, it becomes a hole like excitation. And if you are within this, if you are very close to this gap, then it becomes a it is called a Bogoliubov quasi-particle. It is neither particle or neither hole, but it is a mixture of both of things. It is called so let's see, it is also called Boglons. Boglons or Bogoliubov quasi-particle. Okay, so yeah. So now we see that, so the ground, so let me now draw it in a different diagram. So now you and this is the gap, and this is our ground state energy. So this is our E naught. Okay, or the, so now you see that so to excite a particle, we need to provide it at least this delta amount of energy. So then only I'll be able to reach this excitation spectrum, right? So below this there is no single particle excitation. So below this gap there are only BCS kind of particles. So there can only BCS or Cooper pairs. Okay, right. Yeah. So now if you again look at the expression of this C expression between the C and gamma, so you will see that so this thing will become clear. So my quasi particle is given by this gamma k sigma, so which is now cosine of theta k c k sigma plus sigma sine theta k e to the power I phi and c dagger minus k minus sigma. Okay, so whenever you are far from this Fermi energy, one sec, yeah, so when your, let's say, momentum is much less than Fermi energy, so then you have, what you have is just your gamma k sigma dagger is your sigma c minus k minus sigma. Okay, so it is not a linear combination anymore, it is one of this c, one of these annihilation operators. And if you are beyond the Fermi momentum, then only you have this gamma k sigma dagger as c k sigma. Okay, so it becomes clear that far from the Fermi momentum, this excitations become particle like, and within the Fermi momentum the excitations becomes hole like. Okay, so yeah, so this is I mean this is important. I mean, it is important to really distinguish between the ground state energy and the excitation, okay, which is like many times it is students actually get confused between these. Yeah, yeah, yeah. So I think I am finished with my content. So any questions? Okay, so if not, then we will probably continue next week. Okay, so yeah, so I'll see you then.